Hello everyone and welcome to yet another video. Today I want to start with a little puzzle. So imagine that you are in an interesting store for sports and you are buying t-shirts. The red one, for example, costs $18 and the black one costs $11, and you want to buy a lot of them, but you want to make sure that your total bill is exactly $1,188. And the question is simple. It is how many of each shirt you could have bought. So I said the red t-shirt was $18 and the black one was $11, and the total was something like this. Yes. So what you can write probably is solve it with trial and error, but as developers and software developers and fancy programmers, we want to do it in a more systematic way. So the little puzzle is a classic math problem, and we can write it as an equation. Looks like this: 18 times x plus 11 times y, or y, equals 1188. So this one is called actually Diophantine linear equation, and it can be translated actually as a times x plus b times y equals c. Of course, we are only interested in whole numbers because we cannot have half t-shirt or like 1/10 of a t-shirt. So only whole numbers are accepted in the Diophantine equation. So let's start from the beginning and solve this one with extended Euclidean algorithm. And our goal is to solve this one in Haskell. So it would be interesting to see how we are going to present it in Haskell and how we are going to find a way to solve it without brute forcing, of course, because brute forcing on this one can be easy, but brute forcing on a larger number would be complicated. So let's open Visual Studio Code and take a look. And all right, now we are into Visual Studio Code, like you have seen in the previous Haskell video, and we are going to create a new file and call it ld.hs. So clicking on examples, new file, and calling it ld.hs. LDE stands for Linear Diophantine Equation. Yes, and HS stands for Haskell. So we're going to use the REPL, which is this thing here, and REPL stands for readable print loop. So in Haskell, this thing is called GHCi, which is the Glasgow Haskell Compiler Interactive, and it's probably time to start coding. So let's start with the first thing first. What did we had so far? We had this thing: red t-shirt $18, black t-shirt 11. The total is 1,188. And the question is how many of each. We are looking for the A and B as whole numbers could we buy in order to get the 1188. So in Haskell, when we want to create a new custom type to bundle data together, we use the data keyword. So it should be like this. It's called data LDE2, standing for Linear Diophantine Equation, equals, well, it's already helping us, but in our case, it's going to be like this, equals integer, integer, and then again integer. Okay, so data is a keyword. We are actually here saying I'm going to make a new type. LDE, the first, this thing here says that pretty much this is the name of our new type. You can think of it as bool or a string, but in our case it's called LDE2 because it stands for Linear Diophantine Equation with two variables. Then we have the equal sign, and then pretty much we have again LDE2. That's correct. And this LDE2 is the data constructor, so to say. And this is the function that we will be using to actually build one of our new types. And in the end, we're going to have integer, 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 which is pretty much the types of the values that it will hold. It will hold obviously 3 times integer. Yeah, because integers are useful. They can hold numbers of any size. This is the magic of Haskell. So I guess I know what you're thinking. You're thinking, why did I write LDE2 twice? And this is probably a great question, and it confuses everyone who works with Haskell. So let's think of it this way. The first LDE2 is the name of the type, and this one here. And the second LDE2 is the function you call to make that type. Yeah, so this is the name, and this is the function that you call to make the type. And you'll see this pattern all the time in Haskell. So now I'm going to add one more little thing to this line, actually. And it is going to be something fancy. Let's see whether this one would actually advise. And it advises it's deriving show EQ, pressing tab and enter. It's exactly the way to go. Yeah, I mean, it's auto help here is actually helping a lot. So what does deriving and then show and EQ stands for? It's a bit of Haskell magic for now. In short, show tells Haskell how to print out our new LDE2 type to the terminal in a nice fancy way, or with other words, readable for humans. And EQ tells Haskell how to check if the two LDEs are equal using the double equal operator. This is the comparison operator in Haskell. So this is actually useful. Okay, so far so good. Let's save it and go to the Glasgow terminal. I'm going to call it this way. You can call it the GHCi terminal and see what we can, how we can load our file. Pressing enter, pressing CLS, so we clean everything, and then we say GHCi, and then the name, okay, GHR, and then no, before this we need to go to our examples folder, and there we press GHCi and then LDE. Yes, this is how it works. And now we are into the terminal. So we have one of two modules loaded. Yep, LDHS is the first one, interpreted is the second one. So perfect. Now GHCi knows about this LDE2, and let's see what we can do here. So we're going to use a variable. So I'm going to define the variables with let. Short problem equals LD2. So something like this. I'm not taking the values for granted, just getting them this way. So let's see what we have as short problem. Wow, and short problem already knows that it is of type LD2, and then it has 3 integers here, 18, 11, and then 1188, or if you're non-American, it's 1188. So this is because of this magic for show. And Yeah, it works. So let's create a simple example from that. Pretty much using 1 plus x, 1 times x plus 4 times y, something like this. So 1x plus 4y equaling 3. Question, how many should we have for x and y? I can answer immediately. 1 times 3 plus 4 times 0 is automatically 3. So let's say simple problem would be LD2, and then we should have 1, 4, 3. And if we call it, it would be there. I mean, pretty much so far you can probably be confused because I'm not doing anything. I'm just, in Haskell, I'm just recording integers and then displaying them, nothing else. But it is a step. It is a step that we should go in order to solve our Diophantine, this is how I say it, yeah, Diophantine equation, and it's a linear Diophantine equation. So let's look for a way to solve it. How do we solve it? Let's try to have a type solution to. Yeah. And you see Haskell is already, not Haskell, but Visual Studio Code is already saying integer. And this line says from now on, when I write solution to, what I really mean is a tuple of 2 integers. Yes, as simple as this one. So let's write a function. And the first thing we should always do in Haskell is write the type signature. It's like a contract for a function. So it would be checkSolution. checkSolution, and here we use isA. These 4 dots always stand for isA or is of type, but I use isA. So solution 2, and then LD2, and then bool. Wow, it's actually quite useful. So far so good. We are pretty much saying that in Haskell we are telling Haskell, hey Haskell, or hey GHCi, I'm making a function called checkSolution. It takes one of the solutions to for our XY guesses. In our case, for example, this one was a pretty good guess that actually works. You can check it at home. 1 times 3 plus 4 times 0 is a 3 in any type of mathematics. So back to the point, takes solution 2, then it takes LD2, and it returns a bool. So pretty much it takes this one, it takes this one, and if this one is a solution of that one, then it says true. If it is not, it says false. Yeah, works for me, it should work for you as well. Now let's go to the solution itself. And this is where we would start actually programming something meaningful in Haskell. Not that this thing so far wasn't meaningful, but it wasn't doing anything. We were just recording data and presenting the data, which is as if you are like programming on a paper. You can do the same, like recording and presenting. But calculating the stuff is where our magic works. Okay, so checkSolution XY. Wow. And then LD2 ABC equals A times X plus B times Y equals C. I cannot agree more with the proposal. It works. Imagine that I was the one writing it. So that's that. Let's pause and imagine how great it is. I mean, this is, so to say, Haskell. And let's see how it will work. So what can I say? Take a look at the arguments of checkSolution here and there. Instead of taking some generic variable as solution or equation, we are, in this case, immediately unpacking the variables. So we are telling Haskell, hey Haskell, I know that the first argument will be a solution to tuple, this one, just put the two numbers and call out the first one x and the second one y, which would be quite working. And I know the second argument, this one, would be LDE2, or with other words, linear Diophantine equation with two variables. Just put those three numbers and call them a, b, and c. This should work. And this is the fancy unpacking here. And because we did that, the body of our function after the equal sign is just the math. So to say, this is the body. And our function, as I mentioned, is a Boolean. I really hope you understand and you follow with me. If you do not follow, then probably do this one at home and you can understand it by yourself. Okay, let's continue. So we're calculating the left-hand side and then using the double equals to check if it's equal to the right-hand side, the c. This is pretty much the Boolean. Yeah, this is how the Boolean works. And of course it gives true or false. This is usually what Boolean gives, unless you are in SQL. In SQL it can return also a null, but this is something to do with SQL, and I think it was specific to TSQL or Microsoft SQL. Yeah, doesn't matter. I mean, it was one of the questions for one of the certificates that actually Boolean has three answers and one of them is null. So if Microsoft decided to put it in a certificate question, then it's probably something that you should remember. At least this is something that I remember. So, but in this case, we are not into Microsoft certification for SQL, so a Boolean is only with two values, true or false. So you see this beauty here. We don't have like if statements. We don't have temporary variables. It's just one clean expressive line saying this is how we do it. And I think it's time to test the code. So let's go back to the GHCi and test our file. So pressing Ctrl S to save. And I will pretty much press R, which stands for reload. And now we have it. So let's go back to the simple problem and reload again the simple short problem. Simple problem, short problem. Okay, we have it. So let's test it. Let's check the solution for simple problem. So what do we have to do? Check solution, and then our solution was 3 and then 0. We put them with comma, because see the comma here. I mean, this is something to help. And then we say simple problem, the second argument. And it says true. What about 3-1? 3-1 is false. So 3-0 works. Yeah, quite good. I mean, you can try with 3-3 and simple problem, it will not be working. Yeah. So let's go with the shorts. 18 times x plus 11 times y. Was it like this? Yes. This was like this. And let's see what we can do. Well, it's a bit more interesting. Let's take a wild guess. Check solution, let's say 10 times x and 50 times y. And then we say it's short problem. And we see that our wild guess wasn't good. So this is not a solution. Let's try another strategic guess. What if I only bought large shirts? And by large, I mean the black ones. And no, what was the other one? Red shirts. Yeah. What we can do, we can pretty much say that this would be interesting because we had like 1188 divided by 18. And we see that it is actually 66. So this should be a solution. So let's say checkSolution and then 66, 0 of the other one, and then short problem. Yeah, and it is a solution. And we found one. So 66 of the ones that cost 18, I think the red ones, yes, would be a solution. But yeah, it is good. What about if we go the other way around? Yeah, we only buy the other shirts. So 0 and then 108 would also be a solution, yes. So we found two solutions, and they are actually quite easy just by playing around with GHCi. But this is just because our input data is too easy. And yeah, it's unfair to say that we solved it on the other way. We haven't solved anything because there are probably other solutions. So we need to have a tool to check pretty much the other solutions. But so far we have the solutions that actually work, two solutions that work, and we are sure that our tool for checking the solutions actually also works, which is great so far. So the checking solution works, but let's consider writing it a bit prettier, so to say. This, instead of this LDE 2143 or 1811 1188, let's find a way to write it something similar to this one. So it would be pretty. This way we need a function that is called prettyPrint, and it's also going to be in this solution file. So let's add it. So as I said, prettyPrint, and it already knows what it's going to say. So yeah, and this is great so far. And the rest, okay, I'm going to change it a bit. So it's going to be LD ABC. And here I'm going to put it like this, so it is more visible. So show A++ x, or it would be something like this, times x, yeah, plus actually it should be something like this, plus OP plus space. You're probably thinking, what is this OP? I'll explain later. Plus show. Here it would be using the absolute B. Plus calculation Y, and then show C. Where is, yes, the important part, and where OP B, where, let's see, OP equals to if B is smaller than 0, then minus else plus. Well, pretty much it understood what we wanted to write. This is something probably scary for you if you are new into the AI here with Visual Studio Code, but in general, this is the future, I guess. So we're not going to say to go line by line, although it would be interesting. Pretty much here we are taking the LD2 pattern and matching it to get the A, B, and C, just as we did here, the A, B, and C. And it is building a string with these two pluses. What are these two pluses actually? Imagine Vitosh ++ would return VitoshAcademy. And this is concatenation in Haskell. Yes. So we are using the where clause, and I think this is the first time I'm presenting the where clause in the Haskell course, so to say. And this is another Haskell feature actually, so let's stop a bit on it. Here we are defining a local helper called op or operation. It says it is minus if b is negative, otherwise it is a plus. So let's try it. Let's press reload here, or just R for being faster. And let's say prettyPrint. prettyPrint and then simple problem. Simple problem is not defined. I'll just use it like this. And then prettyPrint simple problem. Variable not in scope, prettyPrint. Okay. Then reload. Yes, finally everything is okay. So this is somehow not that bad. It looks nice. Let's give it a negative example, which is going to be prettyPrint, something like LD2, and then we have the 9. -3, minus is always with parentheses in Haskell, and it works. So the where clause correctly has picked the minus sign. So let's try the short problem. You know what, I'm going to write these two here and there, even without the let, so I can code them like different. I would be able to code them with just a R, and then prettyPrint short problem. Well, it works. It knows everything. So now it is probably time to recap. So let's take a look at what did we do today. We introduced something in Haskell. We took a real-world puzzle about shorts, which wasn't really fancy. We kind of brute forced it, but we made a function in Haskell that actually checks our brute forced solution. And this one here, we were using one of the best, in this function here, we were using one of the best Haskell's features called pattern matching. So what else did we do? We have used our own algebraic data type called LDE2, which is also something, and we managed to test our equation multiple times. For example, we checked the solution with short problem and with what was it, 18, 11, 88, let me see, how was it solved? checkSolution 16600 and short problem like this. And this was the interesting part, that it is checked automatically. Okay, so for the next step there would be more math, because we didn't solve the equation, we haven't showed anything, but this video is already approaching 30 minutes, and I'm thinking of writing a second video where, based on this foundation, we go further and we write the solver. So let's take a look at the second video, and in the meantime, yeah, take some time to enjoy the rest of your day and have fun. So far so good. Goodbye from VitoshAcademy, and let's take a look how we're going to solve the equation in the second video.